right, so on behalf of the co-organisers, who are James Clift and Will Troiani, welcome to the seminar. So maybe I should first explain the title of the seminar. Actually, the next lecture in this series will be devoted to explaining in more detail what the Curry-Howard correspondence is. But roughly speaking, it's one of the key points of contact between mathematical logic, category theory, and computer science, or the theory of computation, if you like. And I'll say, as I said, more about that next lecture and a little bit today. So very much the idea of the seminar series, of which this is the second semester we've been running it, is to explore topics at the intersection of these three areas. And the aim, more specifically this semester, is to understand how to organize mathematical knowledge using topoi. And let me put in brackets and adjoint functors. Okay, so a topos, topoi is the plural of topos. A topos is a particular kind of category. So we're going to have a couple of lectures about category theory later on, and I'll give a brief definition in 10 minutes or so. So they're the basic objects that we're going to be using, and this term organized mathematical knowledge is of course an informal term, and the point of today's lecture is to move a bit closer to having an idea of more formally what that might mean. And of course there are many mathematicians involved in the theory of topoi and the mathematical logic associated to it, and the sorts of ideas we'll be discussing around organizing knowledge. But much of this, the key ideas, go back to Lorvier, in particular the idea that adjoint functors should be somehow a foundational idea in how we organize mathematics, is strongly emphasized by Lorvier. Okay. So let me start with the following sort of picture. So, I guess proto-mathematics, before we sort of introduce concepts, looks like ordered sets, right? So things like the integers with some operation, maybe more than one operation, etc. So, this is about as concrete as it gets. But of course, we very rarely sort of just think entirely in terms of ordered lists of operations on sets. We have various concepts which organize those into similar. Actually, let's stick with each row being its own sort of concept. So maybe let's take polynomials with addition, and maybe the second row is another collection of sets with operations, and those we call rings. All right, so on the very concrete end, we have some ordered sets. Sets with operations, that's what I meant. This column in the middle I'm going to call theories. So this will acquire a precise meaning later on. But for the moment, you just think, abelian groups. The theory of abelian groups is that there's some sort of the abelian group, there's some operations. You can do it various ways, but say you could take addition, the negative, and as constant 0, and then your axioms are some expressions in those data. Okay, and then this passage here is of course very familiar to us. Right? Abstraction, I suppose you could call it. And we organize our knowledge of mathematics in terms of the things in the middle column, right? These theories are how we organize mathematics, typically speaking. So one of the key points in the development of mathematical logic, say at the beginning of the last century, was the idea of turning these concepts, like abelian groups, theorems about them and proofs of those theorems into mathematical objects themselves. Right. Now, from the vantage point of 2018, it maybe seems a little hard to imagine a time when that wasn't the case. But of course, that was a very important step in doing mathematics carefully. And it's important because mathematical objects are the objects about which we know how to reason reliably and how to automate the reasoning about those objects. You know, that's what Mathematica does for us, right? So once theorems and proofs are mathematical objects, we have a much more reliable sort of system of mathematical knowledge. Okay, so that's sort of a general conceptual story. But this seminar is about somehow another step beyond that level of organization. And let me sort of motivate it with a question. All right, so our theorems, definitions, examples, proofs, etc. I mean, the way we typically think about them as working mathematicians, to use a favorite phrase, I mean, they're not organized into formal mathematical objects, strictly speaking, right? I mean, our knowledge about mathematics is organized into things like books, lecture notes, you know, our memories, etc. So that's obviously a very rich sort of informational object, that system of mathematical knowledge, right? And the question we're going to be considering is whether this hierarchical system of mathematical knowledge, to which I don't assign some formal meaning at the moment, is that itself a mathematical object? In the same way that, you know, in the last century we made sense of proofs and theorems as mathematical objects and the subject of mathematical discourse, what about the system itself of mathematical knowledge? Okay, so at a very high conceptual level, that's the question that we're concerned with. Now, I don't propose to answer this question in a one-semester seminar, but we're going to go in that direction, and the key concept which we're going to use to understand this question in a sort of more formal way is, as I said, topos theory. Okay, so what's an example of what I would mean by that kind of system, right? So a system needs more than one thing in it, right? So there's obviously some relation between these two things, right? So there's various ways to make sense of the theory of abelian groups as a mathematical object. We'll discuss one of them, but there's various ones. So let me call that AB, thinking of the theory. So this denotes the theory of abelian groups. This denotes the theory of rings. There's obviously some relationship between them, right? Because in a ring, if I just read off the first two components of a ring thought as an ordered set, sorry, a set with operations, that's an abelian group, right? So there's clearly a connection between those concepts, and the question, well, if this ambitious sort of question can be resolved, we must first resolve a very basic question, which is, if there's a relationship between theories of that kind, well, what is the relationship between these mathematical objects? How to make sense of that? Right? Okay. So what I'm going to explain today is one of the approaches to answering that kind of question, which is based on the theory of topoi. And then we'll end up with a picture which is of the following kind, where we have, well, in fact, it's a two category. I will explain at least what a one category is in a minute, very briefly. Okay. In which these theories will be objects, and there will be some canonical morphisms, between these objects. Okay. Maybe I'll just leave it like this. And this morphism will express the precise relation between these theories, which is encoded in when I point to that first two elements of that ordered triple. Okay, so let's just write something to that effect. So every ring is an abelian group. So this observation leads us to believe there should be transformations or morphisms between theories. Right, so morphism or homomorphism or transformation or relation, right? Somehow there's a connection between these theories. And obviously if we want to answer this kind of question, that is, represent the system of mathematical knowledge as some sort of mathematical object, a crucial point will be, first of all, to settle what we think are morphisms between theories. Right? That seems like a straightforward starting point. Okay. And as I said, so the intention of the seminar is to sort of try and be talking about topics that have some interest to all three of logicians, mathematicians, and computer scientists. So I'll spend some time during the lecture explaining sort of what the ramifications are for this sort of picture. I think the logical interest is sort of clear from the way I motivated it. Maybe it's not clear why topoi, if they resolve this question, whatever they are, I haven't said yet. If they resolve this question, what interest they would be outside of logic. Nor is it clear what the interest is in computer science, but I'll try and say something about all of those. Now's a good time to say briefly what a category is. Okay, so as this lecture is meant to be an overview, clearly there will be many terms that don't get full definitions, but I hope to at least sketch and give you the idea of everything that's going on. So a category is just sort of an algebraic system, a bit like a group or a ring. So it has objects, so you can think of a category as some sort of set. As objects, let's write those as uppercase letters. Between objects it has morphisms. That's the data, but the algebraic operation is a partially defined function called composition. So not any two morphisms can be composed. They can be composed if and only if they have the right sort of domain and target for that to make sense. So the composition rule would take a pair that looks like this. So the pair GF, where the domains and codomains match up in this way, and would map it to some new morphism from X to Y. Oh, thank you, yes. All right, now that's not meant to be, G and F aren't functions necessarily. Often they may be, very often they are not. They're just, I'm given for every pair of objects some set, and part of the data of the category is the rule for assigning this composition to each pair. This is not necessarily data that's immediately obvious beforehand. Okay. So that's what a category is. You can think of the category of all sets, for instance. The objects are sets. Well, okay.
And the existence of morphisms, right?
Sorry?
Existence of identity morphisms.
Oh, thank you, yeah. Yeah, that's right. So dot, dot, dot. Right, so maybe I'll just say it out loud. So the composition should be associative and should have identities. So this is like a monoid with a partially defined composition. Yeah, thanks. So as I said, we'll go through this in more detail in the following lectures. The sort of key example for the moment is sets, or small sets. Let's not worry about sort of foundational issues. So the objects are sets. The arrows from between the sets are just all functions. The composition rule is just composition of functions. And I'll give some more examples in a minute. Okay, so a topos is a kind of category. Sets is an example of a topos. In a minute, I'll give very quickly the definition of a topos, but if you'll forgive me, I'll hold off on that for just one more moment. Okay, so what are we talking about? I'm trying to sketch what it is that topos theory has to say about, well, this step which I erased, this step 2, from theories to categories of theories. So what is the answer topos theory gives to the notion of what a morphism of theories should be? So first of all, topos theory starts from a theory. This is a first order theory, which is, okay, there's some adjectives which need to be added to the front of the word theory. It needs to be so-called geometric theory. These are details I'll get into in a minute. So to some fairly general class of theories, and the theory of abelian groups is an example. There is associated a particular topos. Let's say T. So it's some category with special properties. It's called the classifying topos. So this word classifying I'll explain in a moment. But the idea is first one constructs this category. And then if one wants to know what the set of morphisms between two theories should be, so these are two theories. So HOM is the usual notation in category theory for the set of all arrows between two objects. So things like F. So when I say HOM TT prime, I mean the set of morphisms that we're supposed to be thinking about. And I'm making a definition now. So I'm saying that the right, according to topos theory, notion of morphisms of theories is to first turn your theories into categories and then take functors between those categories. And okay, again, there's some adjective, so one doesn't take all functors, just what are called geometric functors. Okay, so this is, if you like, a proposal for the right notion of morphisms of theories. This is actually not just a set, it's even a category in its own right. So there's also a notion of transformations of morphisms of theories. Okay, so this is what topos theory says, but in order to motivate a seminar on topos theory, I have to, first of all, give you some idea of what these BTs are, why this word classifying, and why this answer is, right. or at least interesting. So I should say that, of course, this topic of organizing mathematical knowledge using category theory, there's various approaches. So this is certainly not, the only way of thinking about these topics. Okay. Maybe this is a good point to pause for questions if there are any. No? Okay.
I have a question. To
Yeah.
build this beaver of T thing, I think it's denoted, the classifying topos.
Yep.
Do we just need the category T, or do we need further data, forgetful functor, that kind of stuff?
Yeah, good question. So the thing we start with, I haven't really said what I mean by a theory, so that's maybe a good place to start. So by a theory, I'm just going to mean some first order language. I'll maybe say more in a minute. And some formulas in that language, which are the axioms. Okay, so it's a purely logical object. So it's, it's usually called a first order theory. Right? Okay, and to that first order theory, I'm supposed to attach a category. So, as those of you who have sort of seen category theory before will not be surprised when my definition is universal property. Okay, but there's also a construction. So I'll say what the universal property is, but you're sort of more asking about the construction. So the construction is to present this in a sort of syntactic way. It's very similar to how you construct a Cartesian closed category from a lambda calculus, right? So the objects of this category will be certain equivalence classes of formulas, which you think of as picking out sub-objects of. So usually, for example, when you construct a category from a lambda calculus, your objects are types, right? So roughly speaking, that's still true here. The objects here are the types that occur in the language T, but you also have to allow yourself to cut out sub-objects of Cartesian products of those types using formulas. Okay, so that's sort of the idea. Roughly speaking, the objects are types, and the morphisms are equivalence classes of terms in the language. So it's a syntactic construction. But it's involved, much more involved in the construction of a Cartesian closed category from a lambda calculus. So for instance, you have to define a Grothendieck topology and take sheaves for that topology. So this construction is sort of intricate, but it has that syntactic flavor. But to come back to your question, it only depends on the language and the formulas. It's not universal relative to some base. So it's just the T.
I have questions.
Yeah.
Is it safe to say that T are just objects in some categories, and those beta, they are just functors attaching to each object?
Yeah, you can say that, right. The problem with sort of that idea is that presupposes that you know what you mean by morphisms of theories already, which no doubt, for example, there are various notions of morphisms of theories, right? Institutions sort of give one, right? So we could imagine that you made sense of a category of theories in which T and T prime live, and then these are purely logical objects, so your notion of morphisms of theories would be something involving the logical data, right? So maybe you need to send every sort here to a sort there, and every constant there to some constant, etc., right? In a way that sort of matched up the axioms, perhaps. The axioms here should go to true statements there, for instance, yeah? And then, as you say, you could think of this beta as being a functor, which would send those theories to categories, and each one of those morphisms defined sort of a priori using just the logical data to an actual functor between categories. That makes sense. Was that what you were getting? That was what you were getting? Yeah. Yeah, I think, so what's interesting about the approach via topos theory is that there are probably more morphisms between these categories naturally arising than you would maybe think of to write down in a definition of morphisms of theories? Actually, that's one of my questions for you guys. So I'm sort of aware of some definitions of morphisms of theories, and those definitions clearly don't get you all the things that you could think about here. But then I'm not so sure whether the things left over are very interesting or not. So this is a question we can sort of think about. But yeah, this is a good way to think about beta, that's right. Okay. So what is the property that characterizes this B of t? This will be one of the main theorems. So one of the main things we want to accomplish in the plan for the semester is A, to construct these guys, and B, to prove this theorem. So I'm fully aware I haven't defined what a topos is, but I'm going to do that immediately after stating this theorem. Okay. So for the statement, just you can think sets. So for any co-complete topos E, there's an equivalence of categories between for any co-complete topos E and geometric theory T. Again, I don't really have time to explain what geometric means. I can explain afterwards if you want to hear about it. Of course, we'll go into detail later on. It includes abelian groups, rings, most of these sort of algebraic complexes of abelian groups, local rings, etc., etc. Okay, so if I've got a theory and a topos, I can look at for the moment, the set of all functors. Oh, I haven't said, forgive me. So let me say what a functor is briefly. So if you think of categories as being some sort of algebraic object, like a monoid with a partially defined multiplication, then a functor between categories is just like a homomorphism of monoids. It's literally what it is. So a functor sends objects. So it has a rule that sends objects of C to objects f of x of d. And morphisms in C to morphisms in D. Let me just say dot, 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 which preserves the operations in a category. What are the operations in a category? Well, you have a binary operation, which is composition. So applying f to a composite should be the composite of f applied to the terms inside. And you have a unary operation, if you like, the identity. So f should send the identity to the identity. So that's what a functor is. Sorry, zeroary operation. That's what I meant to say. Okay, so if I have a co-complete topos E and this BT, I can look at, again, so this is some particular kind of functors from E to BT. So a geometric functor, for those of you who know category theory, this is a functor which has a left adjoint such that the left adjoint preserves finite limits. That's all that means. Okay. Functors from E to BT are in bijective correspondence, sort of, with models of T in E. Okay, so this is the theorem. There's a few things I should explain. So at first approximation, you should think of this as a bijection. So functors from any topos, so think sets. So fix E to be sets, say. Functors from sets into this new object are the same as models of T in sets. Well, it's not quite a bijection, it's an equivalence of categories. So there's some notion of isomorphism of functors, and there's some notion of isomorphism of models, and what's bijective are isomorphism classes of these two kinds of things. Right? Okay, and what is a model of T in E? Right, so I've got my theory, so you could think abelian groups, right? So the theory sets out some objects, some operations, and some laws. And I just take a collection of objects, matching all the objects which are described by the theory, some set of operations with the right arity, and write down diagrams which express the laws, and those diagrams should commute. Okay, so this is one of the things that needs to be explained in more detail, but you should just think of reading the definition of the theory inside the topos E. Okay, but it's about time I defined what a topos is. Okay, so it's a kind of general categorical yoga that once I've said that BT has this kind of property, this property characterizes BT uniquely, well, as uniquely as categories get, that is up to canonical equivalence. Okay, so that's what, so the thing we associate to T is some topos with this property. That is, it sort of knows about all the models of the theory in any topos. So I guess the theorem has two parts. So first of all, there is a topos which satisfies, well, the theorem says, I suppose, that there is a topos which satisfies this condition, right? And we call that topos B of T. Okay, so I'm going to tell you what a topos is, some examples of topoi, and then what the words models of a theory, the theory of abelian groups, in those examples looks like, to give this theorem some context. So a topos is a category with finite limits and colimits. So James is going to explain what limits and colimits are in 2 lectures' time. But for the moment, it just means, for example, that there's a notion of Cartesian product of objects in the category. That's what's relevant for this notion of models. There's an internal notion of function objects. So of course, if z and y are sets, we know what this means, right? The set of all functions from y to z. And in any topos, you can write down the same symbols, and it roughly has the same semantic content. So that is, if I can form Cartesian products of objects in my category, then I can ask for something which has this sort of relationship to Cartesian products, just like it does in sets. And this guy here is called the exponential. So this should be natural in all the variables. And the third thing that it should have is what's called a sub-object classifier. Okay, so a topos is a category E with these conditions. So what's the last condition? So the last condition says that if I take any object x of my topos, I can look at the set of sub-objects, right? So if it's a topos of sets, that's the set of subsets, that is the power set. And that set of sub-objects in that category should be naturally isomorphic to the set of all morphisms from x to some particular fixed object omega. This omega is playing the role of the two-point set in the category of sets. So this is called the sub-object classifier. So that's a topos. As I said, sets is an example, and we're familiar with these structures in the categories of sets. Perhaps the next very important example is sheaves of sets. So we'll go into sheaf theory. It's unavoidable. So the category BT is a category of sheaves in some abstract sense, not in a topological space, but on a small category. So sheaf theory is an important component of the general theory of topoi. But the category of sheaves of sets on a topological space is an example of a topos. For those of you who have seen simplicial sets, the category of simplicial sets is a topos. That's sort of a cheat. The category of simplicial sets is just so it's true that for any small category, if I take the category of contravariant functors from C to sets, again, these words will be explained in more detail in a few lectures. This category of functors is always a topos. Simplicial sets looks like this if C is the category of ordinals, so finite ordinals. So that those categories also give many examples of topoi. And from a logical point of view, an important source of examples is the category of types and terms in any higher order logic. So there's a syntactic way of, given a higher order logic, and by this I mean the way that it's defined in Lambeck and Scott, for instance. So how does this give rise to a topos? Well, as I said, the objects are somehow constructed from the types. Exponentials, well, those are sort of the arrow objects you have in any, like in simply typed lambda calculus. The sub-object classifier, well, this comes from the type of propositions, right? In any higher order logic, there's a type of propositions. That's what makes it higher order. And omega is just that type of propositions. Okay, so that's a way of getting topoi out of logic. All right. I wanted to say what models were. Okay, so for instance, this topos, this guy was implicit, but let me make it explicit. So BT is the classifying topos of the theory T. And by this theorem, the set of all geometric functors from sets into the classifying topos of abelian groups, that's equivalent to the category of models of the theory of abelian groups in sets. That's just abelian groups. Right? If I take models of the theory of abelian groups in the topos of sheaves, of sets on a topological space X, this will give me sheaves of abelian groups. Okay, and well, if I replace the theory of abelian groups by the theory of rings, then I get rings, sheaves of rings. I can get complexes of abelian groups, sheaves of complexes of abelian groups, etc. Okay. Again, the precise way that we make sense of the word model of a theory and a topos, roughly you just follow your nose using what you would write down for sets, but using this categorical terminology, and I'll explain more about that a bit later. All right, so that's the characterization of these topoi B of T. Now what I want to do is go back to this question of how to make sense of a morphism of theories, right? I sort of have in hand now the key idea to do that. But let's think about the relation between the theory of abelian groups and the theory of rings, and which arises from just knowing this theorem. Are there any questions about this theorem maybe before I erase it?
Did Morphisms come up with this as well?
Yeah, that's a good question actually. I don't know. I don't know the providence of the classifying topoi. Yeah, I mean I wouldn't be surprised. Well, often with Lorvier it's sort of cryptically in some some paper somewhere, so maybe I can safely attribute it to him, but I don't actually know where this. The construction is, I mean the proof is not easy, so it's certainly not something that's just sort of, it's not folklore. I think you had to work to prove that. Yeah.
Might be a blurry question, but is it okay to think about that theorem as providing a link going backwards in the
Yeah, you're pointing to an important point, which is that this it sort of seems the wrong way around, right? I mean, usually when we think of models of something in something else, I mean, we think the way my hand just went, right? It's like a map from the thing to the place where the models exist. And in fact, that's correct, and it's because a geometric functor has an adjoint, and it's the adjoint that does the work. Yeah, so this is a very good point. So it's actually my next point, so I anticipated it. Yeah, but you're right. There's something a bit weird about the direction, which is implied by that theorem. Okay, so the first point to make here is that implicit in this theorem is the fact that there's a universal model of the theory T. Right, so models, I mean by model I mean a model of T in any topos. So how do I get some very special object on the right hand side? What should I put on the left hand side? Anybody? Very good, yes. Yes, so someone remembers my class. Right, so if you've got a universal property, you get some special object by always looking for the identity on one of the sides, right? So if I take E to be BT itself, which, well, to be fair, I didn't say that was co-complete, so maybe that's, right, so this is a co-complete topos. So a co-complete means it has all co-elements. So I can take E equals BT on the left, but then I've got some special functor from BT to itself. That is the identity functor. So that corresponds to some model. Let's call it UT, the universal model of T. In BT. Right? So in this topos, there's some, well, for example, abelian group object. Right? So some object together with a binary operation satisfying the laws of an abelian group. Okay, so and that's called the universal model for the following reason. So just the sort of general yoga of the naturality of this isomorphism implies the following very important fact. So corresponding to any model, say M of T in E, right? So think T abelian groups, so M is an abelian group in some topos. Maybe if the topos is sets, it's just an abelian group. Well, this natural isomorphism means there's a unique geometric morphism, let's call it F sub M, from E to BT, okay, so F upper star is just typical notation for so F is some functor from E to BT. It by hypothesis has a left adjoint, which we denote F upper star. So F upper star sends objects in BT to objects in E. In particular, it has to send this UT to something, and it sends it precisely. It's isomorphic to the model M. Okay, so this is, I mean, if you're familiar with classifying spaces, this is where the word classifying comes from. Okay, so this is in response to this question about the direction. It's right that any geometric functor from E to BT, how do I get a model in E out of it? Well, I take the universal model here, and then I send it backwards with the adjoint to get something in E. And that's how everything arises, and it arises uniquely up to isomorphism. Okay, so basically the point here is that these classifying topoi, they're a topos, but they come with some model of the theory, and that model is universal. It's like the Platonic abelian group. Right?
Is there a name for functors whose right adjoint is a geometric functor? If that makes sense.
Yeah, I know what you mean. Well, that's just a functor which has a right adjoint and which itself preserves finite limits. I think given that it's determined by its right adjoint, there's no real need to introduce a new name. But yeah, I think what you're getting at is it sort of feels like the adjoint is the real thing, right? Yeah. But the reason it's presented this way is because, yeah, this is actually an interesting point. So if X and Y are topological spaces, and I take a continuous map, then on the category of sheaves, I have a push forward and a pull back. And this adjoint pair is, so this is a geometric morphism. But because we tend to think that, you know, we're obsessed with sets and functions, this is the real thing, and so the morphism goes that way. So that's sort of why it's, the right adjoint is sort of prioritized. Yeah. Okay, so let me take this sort of abstract point and come back to this question about how to relate the theory of abelian groups and the theory of rings. Right? So, interesting exercise. So, figure out the separated hypothesis, separatedness hypothesis you need on X and Y. So there's actually a bijection between continuous maps and the geometric morphisms. So with some mild condition, they're the same thing. So this is sort of a good reason to believe in geometric morphisms, at least from a topological point of view. Okay, well, every ring is an abelian group, right? This was the fact that we were promised would be manifested in sort of fancy categorical language. So how does this tell us something about classifying topoi? Well, let me consider two theories, the theory of rings, the theory of abelian groups, convert them into topoi. Then, well, this is my E, right? It's a co-complete topos. So the theorem says that geometric functors from E to the classifying topos of abelian groups is the same thing as models of, this is my T, abelian groups in the classifying topos of rings. Okay, but what is a model of the theory of abelian groups in the classifying topos of the theory of rings? Well, we know a model of the theory of rings in the classifying topos of rings, right? So I haven't really spelled out what that means, but so it means that in that topos there's, for example, all the structure maps of the theory of rings are manifested by morphisms. So in particular, the addition on the ring is some morphism in this category, making certain diagrams commute that encode the laws that that addition must satisfy. So if I read out the part of the definition of rings which talks about the addition, Well, what I've written down is a model of the theory of abelian groups, right? So the universal ring, because a ring is an abelian group, the universal ring is, just forgetting about some of the information, a model of the theory of abelian groups in classifying topos. Well, corresponding to that must be some special, let's call it F, some special geometric morphism from B ring to B abelian groups. And as sort of alluded to there, it has the property that its left adjoint sends the universal abelian group to the universal ring. Okay, so this relationship, this logical connection between these two theories has now been realized, so to speak, as a geometric morphism between these classifying topoi. And remember, this was the sort of proposal for the definition of a morphism of theories. You can put this around the other way if you like, right? Okay, but this, we've taken the sort of most elementary connection between these two theories and realized it as a geometric morphism between these topoi. Right. Okay, so the punchline then is the following idea. Coming back to the original question. So the idea is to take as the sort of way of organizing mathematical knowledge this category of theories and morphisms, but really what we're doing is classifying topoi and geometric morphisms. So that's the sort of abstract setting in which we want to pursue these ideas. I should say, of course, this is not our idea, right? This is what topos theory is about for many people. Okay, so I want to quickly make a few remaining points. I want to connect this a bit more explicitly to functional programming, but maybe one observation which will occupy. Yes.
What's the time frame for this thing?
Yeah, well, we should finish in. When did we start? I think it was 10 past or so. Yeah.
Okay.
So I want to finish by then. Yeah.
10 past 4.
Yeah, but I won't be offended if you leave early. So. All right, so one important example which we'll talk about in some length is, so what have I said about these classifying topoi? I've sort of said they can be constructed syntactically. I've given a universal property, but they're still left sort of mysterious, right? What is actually one of these categories for some theory of interest? What is the classifying topos of abelian groups? Is it some category I already know, right? So, in fact, they're very often categories you would have encountered naturally elsewhere, right? That's part of their interest. So if I take the theory of local rings, that's actually the Zariski topos. So this is a very basic object in algebraic geometry. The Zariski topos of schemes over Z. So any scheme, so schemes are spaces for algebraic geometers. any scheme is an object in this topos. So from the point of view of topoi, you just have to say the words local ring, and the Zariski topos springs into existence. Right? So it's kind of neat. Okay. All right. So one of the sort of organization of this seminar will be around the following diagram. So next lecture, so in our first semester we sort of studied this correspondence in detail, and next lecture I'll give a very brief overview. So it's not really necessary to understand the things in this, what we're going to do over the next semester, but it provides the context which sort of explains why it's interesting, the material we're going to look at. So the Curry-Howard correspondence gives a series of bijections between various data associated to particular kinds of intuitionistic logic. Lambda calculi, so these are extensions of the simply typed lambda calculus. And Cartesian closed categories. If you're interested, I can be more technical about exactly what these isomorphisms are talking about. But roughly speaking, the idea is that the content of intuitionistic logic, first order simply typed lambda calculus, so this is sort of a very bare prototypical functional programming language. And particular categories, these are sort of encoding the same ideas. And what we're going to be discussing this semester, well, I've explained the sort of categorical and logical point of view on it. So I've already indicated there's a connection between higher order logic and topoi. And you can think of these topics as being sort of extending the world of functional programs with equations. Right? So if you have some sort of reasoning about or constraints on, say, the input-output behavior of a functional program. And these three things are also, in a sense that needs to be made precise, sort of the same. Okay. Adjectives need to be added at various places, but that's the idea. So these arrows are meant to mean sort of extension. So adding equations gets you to that column. Adding the type of propositions, right, gets you from first order logic to higher order logic, and adding a sub-object classifier gets you to topoi. And we'll be trying to look at all three of those aspects, but sort of primarily these two.
What's this middle? Is this some kind of computer science?
Yeah, actually, I'm not sure to what degree this row has really been studied in these terms. But what I mean here is, so what happens over here is that you can think of, so there's certain kinds of programming languages which are called functional. So if you've heard of Haskell, or there's various other ones. So you can organize the data of such programming languages into categories, where the objects are the types in your programming language, and the arrows or morphisms are your programs. That makes a category, and then it's sort of connected to these other objects. And if you add to that picture, where you have types and programs, equations on programs. So maybe a program, you want to say that, if it's a program that eats integers and outputs integers, a constraint would be that for all integers its output is less than 3, something like that. Okay, so that's an equation in the language which you're using to write your programs, and that's what I mean by this. Yeah, but again, I mean, these connections are not meant to be obvious, so we'll explore some of them. Okay, so I'll stop there, but of course there's time for questions. Yeah.
Is field a geometric theory?
Yes. Oh, well, yes, it is. But there's the way you might write it down at first is not geometric, so you have to be a little careful. But yes, it is geometric. Yeah.
Is there a high-level simple explanation of geometry?
Yeah, it's a good question. I mean, so some parts of topos theory I sort of know very well, but the stuff around geometric I know less well, so I can tell you the definition, but I don't think I can really give you a good explanation. I mean, the reason why, well, you can prove sort of if and only if statements, so certain good things will happen if and only if your theory is geometric, so if you like, that's what the definition means. So the good things are that geometric morphisms are sort of the ones that models, you can pull back models for any two topoi. So so in general, if you have functors between topoi, you can try and take models in one and pull them back to get models in the other, given some morphism between your topoi. But that sort of doesn't work always unless the theory is geometric. So in a sense, geometric is the one. Those are the kinds of theories for which, for any geometric morphism, models can be moved along geometric. For any geometric morphism, you can move models of that theory along the geometric functors. But yeah, it's a good question. I don't think I have a really clear answer to that. So let me just put the schedule up here. Okay, so next week is the Curry-Howard correspondence, and the week after that, Will Traiani is going to talk about monads and how they arise in category theory and computer science. Yeah.
Where does second order logic sit in this?
Yeah. So my higher order logics are all second order. So in a sense, a topos, the language which I'm talking about in a topos has quantifiers in it. But apart from that, it's actually, I mean, this is the interesting aspect really. So how to think about these in categorical terms is sort of what's interesting in this story. Yeah. But it's not easy to say very, very briefly as well. Yeah. That's what you meant by second order, right? Or did you mean like system F second order?
I meant quantification over brackets.
Yeah. Well, so yeah, the only quantifiers we have is things like that.
Okay.
Yeah. So where X is a sort of the language.
Right.
Any other questions? All right. So we'll stop there. Thanks for coming, everyone. If you want announcements about the seminar, please head to my webpage. There's a link there to sign up.